In this presentation, we're going to talk about combined stresses and how stresses can act on a single point in different directions and in different ways, and how those come together and what we do with them. So this diagram that you see in front of you is a canonical example. It's pretty typical. You'll see it in a lot of different textbooks, Norton included. And it's just this idea that we have a bent bar, and let's say, just for clarity right now, that this 8-inch section is aligned with the y-axis, this 6-inch section is aligned with the x-axis, and our force, 550 pounds, is aligned with the z-axis, and that this bar is rigidly mounted at the bottom here. And so the question that we want to answer in order to demonstrate what we want to see in this presentation, the question we want to answer is, how do stresses combine at a single point? And can we use that analysis to figure out the critical points in the structure that we need to analyze to make sure that we can obviate failure in our design or avoid failure in our design? So we can think about this and say, well, if I do a simple thought experiment, this translational force is going to cause, I could treat this 6-inch section and, kind of cut away the rest. And here where this line is here, if I cut it there and act like that's fixed, I have a beam problem. It's just a round beam with a single transverse load at the end, and I know that then there would be a reaction load here in the opposite direction equal in force, so you'd have a 550-pound load here, transverse, and then I have a bending moment here as well, equal to 550 pounds times 6 inches. So I can think about that and think, well, okay, if I recall correctly, transverse shear is 0, where my bending stresses are going to be maximum. So I'm going to have either a maximum bending stress or a transverse shear, but not really both that combine in a meaningful way that's going to cause a higher state of stress. In that case, usually bending stresses will dominate. This is something that you've seen in strengths of materials. If you were just to take a 6-inch beam, fix one end, and put 550 pounds on the other end, that's what you have. Now, this is interesting because what we have here is totally different. I have an extra moment arm here. So this 550 pounds is not only causing a moment about the y-axis, which on this 8-inch section is a torsion, but it's also causing a bending moment in the same way, because that 550-pound reaction is translated over to here. So I still have a bending moment here as well. So I have some maximum stresses at A because of the bending moment, and then I have some maximum stresses at B because the torsional stresses may combine with my transverse shear, and we'll take a look at that. So we can take a look just kind of methodically at a part and say, here are my critical points that I need to look at, and then examine how those stresses are combining. And this is an important part of the design process, where we have to kind of intuitively identify those areas where we're going to see those highest levels of stress. Sometimes it's not as straightforward as that, and you might need to use a finite element code or something to give you a more detailed picture, but even then you need to verify that code. So getting this skill of, or honing this skill rather, of trying to locate those critical points is very important, and you can practice that. There are practice problems in the various textbooks that have been provided to you for reference, or you can look at many examples online or through Sham's outline. Point is, we're going to look down here at the bottom because we have a torsion, or what is a bending moment at the end of this beam around the 8-inch section is a torsion. I have a bending moment because of this force, this transverse force, and then I have a transverse shear at the end that's causing a shear stress. And so those three things are going to combine, and so we're going to cut this at the bottom and then take a look at the different stresses. So again, what we have here is a transverse force that's going to be 550 pounds in the negative z direction. Again, I'm looking up from the bottom of this 8-inch section, and we can see how we've kind of changed our axis orientation here. So we've got a 550-pound reaction force in the opposite direction, so it's negative z. I've got a reaction torque that is going to be in the opposite direction, and according to the right-hand rule, that's going to be in positive y, my reaction. And then I've got a reaction bending moment here because this is rigidly mounted, and that is about x, and according to the right-hand rule is going to be a negative bending moment reaction there. And so these three things are each going to independently cause stresses, and then we're going to pick points on this cross-section in terms of where those things are maximum. To reiterate, just because this is a very important point, we can see that the transverse shear, if you think intuitively again, my transverse shear across this cross section is going to be constant. And across this cross section, it's also going to be constant at a 550 pound reaction. That means that my bending moment here, about, in this case, that would be about y. The bending moment about y is going to be maximum here at this end. In this part of the beam, that's actually going to be a torsion, and then I'm going to have that same torsion all the way down the cross section. So we've got a transverse shear that's constant along the cross section of the 8-inch section. I've got a torsion that's constant along the axis of the 8-inch section. And I've got then a bending moment that is maximum here where it's mounted. And so we can kind of zero in on this is probably the cross section I need to focus on, because these two stresses, the transverse load and this torsional load, are the same anywhere along here. And so this bending moment is the one that's going to change the state of stress and increase that state of stress at this point. So we've got these three loads. Let's calculate them and look at how they combine. So let's take a look at this torsion. We have the torsion about the y-axis that's induced by this load. So again, this load causes a bending moment down here that, as I look at this 8-inch section, is then torsional because it's around the longitudinal axis of that beam. And it's equal to r cross f. Torque is equal to r cross f. That hasn't changed from basic physics. In this case, we have that our 550 pound load is perpendicular to our 6-inch section here. So it's a very simple 6 inches times 550 pounds. There are no angles involved. And so we can solve that the torsion about that is going to be, what is that, 3,800 or something like that. We'll calculate it later. But notably, we recall that our stress distribution across the cross section due to a torsion in a circular member. And by the way, for non-circular members, this is totally different. In fact, it's non-uniform. In non-uniform cross sections, sometimes the distribution due to a torsion is actually very difficult to describe. Some of them are analytically solved problems that you can just plug and chug into a formula. Others are approximations that we need to solve with finite element code. So in this case, a round shaft makes this easy. And for a round shaft, circular cross section, the torsional stress distribution, the shear stress distribution due to torsion, is maximum at the outside. It is constant regardless of where you look at it on that circle. Of course, it's symmetric, and so we would expect that. That makes sense. It's 0 at the center. And so we have that our maximum shear stress due to a torsion is the torque times, in this case, the radius, the maximum distance from the neutral axis, divided by the polar moment of inertia, in this case, pi r to the 4th over 2. Now, one thing to remember, and we'll go over this when we go to combine this with the other stresses. If I look at the torsional stress here on the x-axis, so if I'm looking at it, this is kind of rotated 90 degrees. So this x point correlates to this point right here. This z point correlates to this point right here. We remember that for a torsional stress, we have to keep our axes straight. If I look at the torsional stress at where this cross-section crosses the x-axis, so this point right here, which, if I recall correctly, is point B as we're looking at it, at point B, the shear stress planes involved are different than at point A, here where we cross the z-axis. So remember always that the torsional shear stress includes the two axes that are not the radial axis. So here where we're crossing the z-axis, where the z-axis is radial from the center of the circle, we know that we're going to have tau xy. So at point A, I'll have a tau xy, but at point B, that's on the x-axis, so I will have a tau yz. And this is significant if we're trying to remember where to combine our stresses. When we start to build that stress tensor, remember that constructing a combined stress at a single point, you have to be consistent about your orientation. Otherwise, the whole thing just goes to pot. So we have our stress distribution due to the torsional stresses. Our maximum shear stress is going to be the same at point A as it is at point B, just aligned to different axes. And we'll get to that as we combine those stresses. We also have a moment reaction. So we have a bending stress due to this bending moment. Again, our moment is going to be calculated with a simple r cross f, where in this case, the moment is this translational force times the 8-inch distance that's causing a bending moment on our 8-inch section. Just like a normal beam problem, you've probably seen this a dozen times before. In this case, we have our moment about x, and as we said before, it's negative, and it's 8 inches times 550 pounds, because again, the 550 pounds is exactly perpendicular to our beam. And so to remind ourselves what the stress distribution looks like due to a bending moment, we have compressive stresses here on the side with the z-axis. So we have compression over here, and we have tension on this other side. And so that'll matter because we have positive, negative, and if we want to combine stresses, those things are important. And so in this case, we have, again, if we were to orient it to the original diagram, we have compression here, and that makes sense because if I were to just grab this thing and pull it this way, then I'm going to compress this side of the beam, and then this far side of the beam I'm going to be stretching. And so I've got a maximum stress, MC over I is going to be my maximal stress, where the bending moment reaction is this negative 8 times 550. C is the maximum distance from the neutral axis for this circular beam. It's going to be R again. And I is the moment of inertia, area moment of inertia, pi r to the 4th over 4. So we've seen this, of course, a number of times. And we must remember that across this entire cross section along the x-axis, because that's the neutral axis in bending, so it's this axis here in bending, the stress there is 0. So we have no bending stresses at point B, but we have maximal bending stresses at point A, but they're compressive. Now, how that works with a combined stress, we could check at the opposite of point A, so over here on the back of the cross section, and we would see from both of the failure criteria that we'll talk about in a later slideshow that those two will actually be equivalent, but that's kind of beyond the scope of this discussion. But at any rate, we have a bending stress distribution, should look pretty familiar, and so we're going to have bending stresses at A, but 0 stresses at B, again because of the neutral axis. We're also going to have transverse shear, and we have to consider this. We have to remember that if we cut right here at the wall, that I do have a shear reaction due to that transverse shear. So if I were to cut, just infinitesimally away from the wall where that reaction force is, then our transverse shear, as we'll recall, is 0 where my bending stresses would normally be maximum. So here at point A and then kind of across from point A. Those 2 points, my transverse shear is going to be 0, but it's going to be constant in lines along the x-axis across the cross-section. And so that distribution is going to be parabolic, and the transverse shear then is going to be maximum along this x-axis. So we're going to have a maximum shear stress due to transverse shear here at B, and we're also going to have my maximum torsional stress, which is the same at A and B. And so I've got bending plus torsion here, I've got transverse shear plus torsion here. And of course, because it's 0 at A, the transverse shear is, there won't be any in the A matrix. We have solved this problem many times over. We know that tau max due to transverse shear, again, because of the reaction force, this is the internal shear, not torsion. We have the equation because this is a circular cross-section of 4V over 3A, where V is my reaction force, in this case negative 550 pounds because it's 550 pounds negative in Z, and 3A where A is pi r squared, the cross-sectional area. And so we can calculate those as well. So let's take a look at our actual combined stresses at point A and B and see which one is greater. That's going to be a little bit difficult to do. We're going to have to kind of go a little bit outside the scope of our discussion here, but it's, bear with me. I think you'll find that this is not terribly difficult to understand. So let's go ahead and construct our stress tensor at point A. At point A, we have this stress cube effectively aligned to these axes. And so we have a compressive stress in Y because of bending. So that's our axial stress here along the y-axis. And then we have a shear stress along the y-x-axis. So remember that at point A we said that that's aligned to the z-axis, and because this is a point on the z-axis is radial here, the two planes involved in shear are then going to be x, y. So it's, the two non-radial axes are going to be involved in our torsional shear. So we have tau xy is going to be negative Tc over J, and our stress in the y direction is going to be compressive, is going to be MC over I, where our moment, of course, is negative. So we can combine these using a criterion called the von Mises criterion. So the big question is, what do I do? I have up to 9 numbers here, really 6 independent numbers here, to try to quantify. How do I compare one state of stress to another? To really oversimplify it, we can do that using the von Mises criterion, which is an equation that we'll be going over in detail, but I can come up with one number that sums up this total state of stress, all six stresses, in one number. And the higher the number, the higher the effective stress in that element. So in this case, if we put our numbers in here for MC over I and TC over J, we come up with what we call an effective stress at point A of 53,442 psi. We can calculate that number and see how that works. And so we have 53 ksi-ish at point A. So we'll compare that then to point B, which will be a different stress state. So just to go over it one more time, we have shear stresses, tau xy. Remember that in this stress tensor we have sigma xx, sigma yy, sigma zz, tau xy, tau xz, and tau yz, and these follow the orientation with which I'm looking at that element. And so I might come up with, actually necessarily, if I rotate my frame of reference, I'm going to get a different stress tensor, but the state of stress, things that are summed up with criterion such as the von Mises criterion, that state of stress would be no different. I could rotate my axes 37 degrees in one direction and 42 degrees in another direction and construct a stress tensor, and it would look totally different than this. But if I took the von Mises effective stress, I would get the exact same number. So just bear that in mind when we're looking at these stress tensors. So let's look at point B. At point B, we have only shear stress, and in this case, we've got our transverse shear, which is in YZ. Again, the radial portion of the torsional shear is going to be, the torsional shear is going to be off the radial axis. And so in this case, the radial axis is X. So we have a tau YZ for the torsion at this point, and we have a tau YZ due to the transverse shear at this point as well, because the transverse shear here is in the Z direction. And so here we have these two combining. Of course, if we looked at the opposite point from point B, we would have one minus the other, so they'd be kind of canceling. So point B is going to be greater than the opposite side of the cross-section from it, whereas with the bending moment, that's not exactly the case because they're different stresses. But because we're combining those shear stresses in the same direction, we will have a higher shear stress at point B than we will for that point across the cross-section. So constructing our stress tensor again, we have no axial stresses. All we have is tau yz, and we have our torsional component here, TC over J, plus our transverse shear component, 4V over 3A. We can combine those again with the von Mises effective stress just to get it to one number, and we get 30.7 KSI, significantly lower, which is not terribly surprising. If we have a constant transverse torsional stress, and then we have a transverse shear and bending moment that are just like a beam problem, we remember that the bending moment stresses are generally going to dominate, and as a result, the transverse shear and the way that it combines with the torsion is still probably not going to be enough to enough to outweigh that bending stress in the way that it combines with it. Regardless, we can quickly see, just by picking a couple of points, the different stress distributions and their sum total effect on that given element. So, of course, we picked an element here at A and drew it, constructed the tensor, found an effective stress. We do that for all the critical points, all those points where we think, I need to assess the stress at this point because I'm not sure which one of these is going to be greater, but I can basically do a little bit of a thought experiment to say, well, the stresses here are going to be greater than the stresses here, and the stresses here are going to be greater than the stresses here. So let's pick some points on this cross-section here, and based on what types of stresses those are, I can pick my critical points, construct my tensors, and then, as we'll see when we go over plastic failure criteria, I can sum that up in a criterion that I can then compare to a fixed yield point. And so that's how combined stresses work. we have to remember that combined stresses and combined forces, etc. If I were to put some other force on here, I have to remember to do my shear and bending moment diagrams to make sure that my stresses are already calculated. In other words, I can't just like take one state of stress at B and then simply add it to some other state of stress due to a totally different load. I need the loads to balance first, and then I can go and calculate my stresses. So that's how combined stresses work. This is one example of many. You'll find some in your reference texts. If you look up some examples on Sham's outline, etc., you'll find some others. But this is probably one of the more common examples out there. And so once we are able to calculate combined stresses at a point, we can then take those into our plastic failure criteria and really dig into design and then revising this design based on this information.